We're going to do more notes. I know. We're going to get started. We are trying to catch up a little bit from all the games and shenanigans we did before the break. So again, a definition that we had before, a stationary point is where the derivative is 0. And we talked about the types of stationary points already. There are 3 of them: maximum points, minimum points, and stationary points of inflection, which shows up on an x-cubed graph, where the derivative is equal to 0 at that point, but it actually doesn't change from positive to negative as far as the slopes go. So we're going to be able to tell you have a maximum point when the following happens. First of all, the derivative is equal to 0, but that doesn't tell us it's a maximum or a minimum. It tells us it could be either, it could even be a stationary point of inflection. But if before where your derivative is 0, if your slopes are positive before and negative afterwards, the only way that can happen is if you have a maximum at that point. And if your derivative changes from negative to positive, it has to change from decreasing to increasing. The only way that could happen is that it is a minimum. And if it stays increasing, goes increasing, increasing, or decreasing, decreasing, if your derivative doesn't change, but it's equal to 0 in between, that's where you have a stationary point of inflection. You're going to find out later when we study inflection points. This is a special kind of inflection point. But if you think about how do we use the word inflection if someone changes their inflection, the way they're talking, right? It has something change about it, right? So in graphing, an inflection point tells us where the curve is changing. And this curve changes from being bent downwards to being bent upwards. And whenever a graph changes its bend, we call it an inflection point. It changes its concavity from concave down to concave up. So that's what an inflection point is. A special kind of inflection point is called a stationary point of inflection because it's also where its derivative is equal to 0. We have relative maxes and mins and absolute maxes or mins. Okay? Somebody in this class is the tallest. Somebody in this class is the shortest. In this class, the tallest person would be a relative maximum because they are the tallest person in this class. But they're not an absolute maximum because I'm pretty sure there's taller people in the world than the tallest person in this class. No, I am the absolute tallest person in the world. Right. But we also have a relative maximum tallest person in this row. So, yes, if we go rows this way, Alice is the tallest person in this row, and that's why we use her answers for the answer key. Because she is always right. Your row, that, I don't know, what do we? Okay. The first derivative test. There are two derivative tests. They both find maximums and minimums. One finds the maximum or minimum using the first derivative. Another finds a maximum or minimum finding the second derivative. So the first derivative test says that you will have a relative maximum or a local maximum at the critical point if the derivative changes from positive to negative. Here's your critical point C. And if you had a derivative that was positive before it and negative after it, our number line would say it is increasing, then decreasing. And if a point exists at C, in other words, it's not a non-permissible value, the only way that that can happen is if that point C, you have a maximum. This is the first derivative test to find out if something is a maximum. If at point C, you go negative before and positive afterwards, it would mean your graph was decreasing, then increasing. Then you would have a relative minimum. And I find the first derivative test really intuitive, especially if we draw our arrows on the number line like that. There is a second derivative test. Maybe you make a note. No, there's just two. Can we make up one? I just keep giving you tests. This is the third derivative test you have to do for me. There will be two derivative tests that we do. This is the first one. So you're getting into what you're thinking, okay? Like the first derivative test just uses the first derivative, but it is for finding maximums and minimums, okay? The first derivative is used to find increasing and decreasing. And one of its side benefits is you can tell quite easily where a maximum and minimum is. In order to say the first derivative test, you need two pieces of information. You need to first show that it's a critical number. In other words, the derivative is equal to 0. And then secondly, you need to show that it's changing either from increasing to decreasing or decreasing to increasing. And that wording is shown up here. You will get confused with the second derivative test when we get to it. So it's trying, yeah, and I will try to be extra explicit when we get to the second derivative test. Because the second derivative tells us where things are concave up and concave down. The second derivative will go into inflection points. But the second derivative test is a way to show maximums and minimums. And most people don't like it because they like the first derivative test is so easy. Why would I want to ever do a second derivative test? So you have a local maximum when it changes from increasing to decreasing. And you have a local minimum when it changes from decreasing to increasing. And the arrow graphs really imply, oh, what do you think? Should that be a maximum point or a minimum point? Oh, what do you think? Should that be a minimum point or a maximum point? Well, the arrows mimic the graph, so it's really easy to tell where something's a maximum or a minimum. Well, I don't know, Aiden. Everything is relative. So just a show of hands, how many people would like to see Aiden write the next test upside down? We can tie him from the ceiling so that we have the exact rope so you can still reach your test, but you have to do it upside down. Oh, it is a challenge. I'll just turn this off.